we are given this predator-prey system. Dx over dt and dy over dt is like this. So x and y represent the population of the predators or prey population. So without even they tell us which one represent predator, which one represent prey, we can tell from this equation. So look at this x. This is how the population change over time. This is how the population of y changes over time, and they interact with each other from this term xy. So we see that when for the x population, when there is a presence of y show up and they interact, the population of x decreasing. So that is, so x, we can tell this must be prey, because when y show up, the population of x decreasing. When for the y species, so you see that when x show up, the population of y is increasing. Okay? Just plus something, y times x. So this one, y represent the population of the predator. Yeah. And another note is that you look at this. We say that x is logistic because it has a term minus x squared here. So you see that this one, when x small, this term is not, it is small. But when x is big, x squared is really, really big, much bigger than 8 times x. So it will die out when x is big. So there is an upper bound for this one. You think of that, let's say animals. The animals of the same species will compete with each other, maybe over the environment. Maybe they don't have enough space to live. Maybe they don't have enough resources to live. So that's why there is an upper bound. They cannot just grow, continue growing forever. X population, this one is logistic. And for this one, for the predators, when there is no prey. So for example, if you don't see this term, they continue dying out. If they don't have food, to say, if they don't have enough food, or we don't have this term, then it keep decreasing. Okay, now we need to find the critical points. The critical points are the points x, y, so that the derivative are 0. So we need to solve the system of equation. This one equal to 0, and this one equal to 0. The second equation will be easier for us to start. Here you see that y in common, x minus 2 equal to 0. Therefore, you have two cases here. Case 1, y equal to 0, and case 2, x equal to 2. So for y equal to 0, you just plug in the first equation. You have 8 times x minus x squared minus 0 equal to 0. X times 8 minus x equal to 0. So either x is 0 or x equal to 8. So we have two critical points right here, 0, 0, and 8, 0. For case 2, you have x equal to 2. X equal to 2, you plug in the first equation. Uh, 16 minus 4, 2y, 0. So we have 12 minus 2y, 0. Y equal to 6. This gives us another critical point, 2, 6. So now we have 3 critical points. So they are on isolated critical point. We look at the behavior of those or around those critical points. So we determine the type and the stability of those critical points. These are all, so we have the almost linear system. So we will linearize it. So let's look at consider 0, 0. Consider the critical point 0, 0. For this question, let me compute the Jacobian matrix for the general case, and then we can plug in the values x, y at each of the 3 critical points. So this is a system they give us. Jacobian matrix df over dx. Let's go, f is the first equation and g is second equation. F y g x g y. So the first one is fx 8 minus 2x minus y minus x y minus 2 plus x. This is a Jacobian matrix, and we consider critical point 0, 0. Now plug in the value for that Jacobian matrix at 0, 0. In our case, for x is 0, 0. 8 minus 0, so 0, 0 minus 2. This matrix is diagonal. You see that two eigenvalues right here. 8 and minus 2 correspond to that with two linear independent eigenvectors. So eigenvalues 8 and minus 2, so they are real of opposite side. So for sure that 0, 0 is a saddle point, unstable saddle point. So you see that 0, 0 is a critical point of the linearized system U prime V prime equal to Jacobian. Let's call it Jacobian 0, 0 to differentiate with the two other Jacobian UV. And U and V here are actually equal to X and Y. So this critical point 0, 0 of this linearized system is a saddle point. It is also tell that the 0, 0 critical point of the original system is also a saddle point. So 0, 0 critical point of the original system is a saddle point. Here we want to look at what happens surround that we compute the eigenvectors and see. So in our case, we know that we have two linearly independent eigenvectors. The first one, we can choose them to be 1, 0 and 0, 1. So 1, 0, this gives us the first 8, 0, the first column, 1, 0. So 1, 0 is eigenvectors correspond to lambda equal to 8, and the other one, the eigenvectors say lambda 1 equal to 8, V1, 1, 0, the other one, lambda 2 equal to minus 2, V2 is 0, 1. So this is eigenvalues and eigenvectors. We can sketch what happened surround 0, 0. We know this is saddle point. Lambda 1 equal to 8. V1. So V1 like this, and we have this x-axis, and on that axis lambda is positive, so everything go outward. Second one is lambda 2 equal to negative 2. Negatives, so it's go inward. Eigenvectors on this one, but it's go inward because negative lambda here. So around us we have Soren curve would look like this. So this is around 0, 0. Now let's look at the second critical point, which is 0, 8, 0. So by the way, this 0, 0 or this critical point 0, 0 correspond to the points where the population of two species are both 0. They both die out. So total extinction. The second one, 8, 0. So we have one species, the prey we have 8, and the predator is now 0. At that critical point, we all have the prey survives. Now we compute the Jacobian matrix at that point. Jacobian matrix is given by this matrix. Now we evaluate it at 8, 0. 8, 0. So we have 8 minus 16 minus 0 minus 8, 0 minus 2 plus 8. See that we have two eigenvalues, minus 8 and 6. So opposite side they were real, so we have another saddle point. So the critical point of the linearized system, or the critical point is 0 of the original system, it's 0 of the original system, say 1, and or 0, 0 of the linearized system, of the linearization at 8, 0 is a saddle point. And if we want to sketch the phase diagram, we compute the eigenvectors. So the first one, we know that corresponds to minus 8, we should have 1, 0. If you multiply 1, 0, get the first column. Minus 8 times vectors 1, 0. So we see that 1, 0 is an eigenvectors correspond to minus 8. Lambda 1 equal to minus 8. V1 is 1, 0. For the other one, lambda 2 equal to 6. We need to solve that. So this one minus 6, minus 14 minus 8, 0, 0 equal to 0. So you have 7, A, 4, B, 0. A, let me choose A to be minus 4 and B to be 7 is good. So we have one eigenvectors V2 minus 4, 7. Around 0, 0 of the linearized system. You have, what is this? 1 0. 1 0 is here. This gives us the axis, x-axis. 1 0 will correspond to -8, so everything go inside. The second one would be -4 7. -4, let's say -4 is here. Let's say 7 is here. -4 7 will give us this line. Lambda 2 equal to 6 V2 -4 7, and because this is positive lambda 2, so we have, let's go outward. So diagram, so the other solution could go like this. This 1 0 0 of the linearized system be a saddle point, and that correspond to 8 0 is a saddle point. Of the original system. And then if you pick the regions around it, you see this behavior. Now we look at the last critical point. The last critical point is 2 6. Now look at the Jacobian matrix at that point. Jacobian matrix at the 2 6. So we have x equal to 2, y equal to 6, 8 -4 -6 -2 6 -2 plus 2 -2 -2 6 0. We have to compute eigenvalues. -2 minus lambda -2 6 minus lambda. Lambda plus 2 12. Lambda square 2 lambda plus 12. So we need to compute the root of that. Square root -11. So we have lambda 1 2 -11. So we have -1 plus -I square root 11. So that's 2 6, or correspond to that 0 0 of the linearized system. Is a spiral point. In this case, the real path is negative, so we have logically stable. And if we want to sketch that, let's compute 1 0. So let's see what it does. The matrix, this matrix act on the point 1 0. So we know that it will give us the first column minus 2 6. So we know the direction. Here's 1 0 minus 2 6. So it should give us these vectors, and you see that gives us the direction is parallel to that of the same direction. So the spiraling would be, we know that is spiral point and asymptotically stable. Spiral inward, the origin to the origin, because the real path is negative. So we know that spiral inward toward the origin. So I just sketch this, it should look like this. And here's one solution curve. For the big picture, if we use computers to sketch the graph, you see 0 0 is one critical point, 8 0 is another critical point, and we have 2 6 8 here, 0 2 6, we have another critical point here. So around 0 0, you see that we have a saddle point look like this. So around 0 0. This is what surround 0 0 look like. Correspond to 0 0 of the horizontal system. The second one, 8 0, is a saddle point. 8 0. We should expect something like this around 8 0. And we have a spiraling I should delete all the axes. Spiraling here around this point. Yeah, so this what we expect to see general picture. Now let us try to connect them together. So we should have the connection like this. Then the saddle point here, right? It just go up like this. That's how we expect to see the direction field in the solution curve. And actually, because we look at the population of two species, so the population is always non-negative, so we focus on this region, but the other one, you can just connect them like that. Saddle point right there. For this part, it should go like this. So for example, direction would look like this. If we plot the phase diagram with the computer, we should see the big picture look like this.